Welcome to this explainer. We're diving straight into the pursuit of absolute precision in Class 12 electrical practicals. For all you focused learners out there, we aren't just going to sit here and memorize formulas or talk about how to avoid burning our fingers on a hot rheostat today. We're actually going to uncover the elegant and, quite frankly, brilliant physics hiding right behind those bulky wooden lab boards, the tangled connecting wires, and those sliding metal jockeys you're so used to seeing. By the end of this explainer, you're going to understand exactly how to manipulate these classic tools to achieve some seriously absolute precision. So here's our roadmap, which is basically going to serve as your ultimate cheat sheet for mastering these crucial lab stations. We've got 1, the null point magic; 2, mastering the meter bridge; 3, calculating specific resistivity; 4, potentiometer versus voltmeter; and 5, measuring internal resistance.
All right, let's jump right into Section 1. The null point magic, or what I like to call the measurement paradox.
We're starting here because we really need to address a fundamental flaw that plagues standard laboratory tools. Think about this. Why does a standard voltmeter actually change the very voltage it is trying to measure? I know, it kind of sounds like a trick question, right? But it's absolutely true. A traditional voltmeter has finite input resistance. Because of this, it literally has to draw a small amount of current from the circuit just to move its physical needle or power up its digital display. And the exact moment it draws that current, it alters the circuit. It causes a voltage drop across the cell's internal resistance, which means the meter only ever displays the terminal voltage under load, and that is always slightly lower than the true original voltage. So obviously, we need a better solution.
And here is that beautiful solution captured perfectly in this principle. No current flows between 2 points at the same potential. This is the whole null point concept in a nutshell. Just imagine a perfectly balanced seesaw. If the pressure on both sides is exactly equal, nothing moves. Well, in our electrical circuits, if we can perfectly balance an unknown voltage against a known reference voltage, our galvanometer needle just drops to zero deflection. At this exact point of balance, the measuring instrument draws absolutely zero current from the source. It observes the circuit without disturbing it at all. It's almost like magic.
Moving right along to Section 2, mastering the meter bridge by applying the Wheatstone principle.
Now, when we take that null point magic and apply it to our first physical lab setup, it brings us to the classic 19th century Wheatstone bridge circuit. Quick fun fact for you, it was actually originally proposed by Samuel Christie in 1833, but it was later popularized by Sir Charles Wheatstone. The setup features 4 resistors arranged in this diamond shape with a sensitive galvanometer connecting the midpoints, which acts as a bridge to detect any current flowing between the 2 branches. And this setup brings us straight to the Wheatstone balancing condition. When the bridge is perfectly balanced, the ratio of the resistances in one branch perfectly equals the ratio in the other. When this happens, the potential difference across that central galvanometer is a flat 0. That middle path essentially becomes entirely invisible to the current, and that allows for incredibly precise measurements of an unknown resistor without even having to worry about the internal resistance of the power supply.
So, how does this actually translate to the physical actions you have to take at your lab station to find that perfect balance point on a meter bridge? Well, first, you're going to connect your unknown resistance X in one gap and a known resistance from a resistance box R in the other gap. Then you simply take your handheld metal jockey and gently slide it along the 1 meter long constantan or manganese wire. You just watch the galvanometer closely until you find the exact, precise point where the needle rests at 0. The crucial takeaway here is this simple formula. X equals L1 divided by L2 multiplied by R. Because the wire has a uniform thickness, its resistance is directly proportional to its length. This means by simply measuring the length of the wire on the left side of the balance point, L1, and the remaining length on the right, L2, you can completely solve for the unknown resistance. You don't even need to know the exact current flowing through the main circuit. It's a really elegant shortcut. Let's transition over to Section 3, calculating specific resistivity, going way beyond simple resistance. Now that we've found our resistance, we can use it to discover an intrinsic property of the material itself. We're talking about specific resistance, or resistivity, which is represented by the Greek letter rho. The formula is pi times radius squared times our newly found resistance X, all divided by the length of the wire, L. Now remember, while resistance changes depending on how long or thick a wire is, resistivity is a fundamental, unchanging characteristic of the metal itself.
To find it, you just measure the physical length of your wire sample with a standard scale, and then use a screw gauge to find its radius. Plug those exact numbers into this formula with your resistance X, and boom, you've unlocked the material's specific resistivity.
All right, section 4, potentiometer versus voltmeter, the search for the true EMF champion.
We are really raising the stakes now by looking at voltage. We're pitting our bulky, seemingly old-fashioned lab potentiometer up against the sleek, modern digital voltmeter. Remember that measurement paradox from earlier? A voltmeter is totally quick and easy, but because it draws current, it can only ever measure terminal voltage under load. The potentiometer, on the other hand, utilizes our null point magic. It compares the unknown voltage against a known reference along a resistive wire. At the exact moment of balance, it draws zero current. Nothing. It doesn't rob the circuit of a single electron, meaning it measures the true, pure, open-circuit electromotive force, or EMF. For pure accuracy, it's the undisputed champion. But what if you want to measure the tiniest possible potential difference, like an incredibly weak signal? For that, you need to maximize the potentiometer's sensitivity. You do this in two specific ways. First, decrease the potential gradient by using a rheostat to reduce the main circuit current. Second, increase the length of the potentiometer wire. This is exactly why laboratory potentiometers are so ridiculously massive, with wire folded back and forth across huge wooden boards that are often 4 to 10 meters long. Basically, the longer the wire, the more sensitive and precise your measurements become.
Which brings us to our final stop, section 5, measuring internal resistance and comparing EMFs.
Here, we apply the potentiometer's zero-current superpower to analyze the internal workings of battery cells. But before finding internal resistance, we can quickly compare the EMF of two different cells, like a Daniell cell and a Leclanché cell. Because the potentiometer balances voltage perfectly against wire length, the math is incredibly straightforward. E1 over E2 equals L1 over L2. You literally just find the balancing length for the first cell, flip the key, and find the balancing length for the second cell. The ratio of those two physical lengths on your wooden board gives you the exact ratio of their electromotive forces. Now let's talk about internal resistance, usually denoted by a lowercase r. It is critical to understand that this is an intrinsic property of the cell itself. It's the actual resistance against the flow of current caused by the chemical electrolyte, the temperature, and the physical distance between the electrodes inside the battery. It absolutely does not depend on whatever external resistance you apply to the circuit. To calculate this, we use a majorly important formula for your practicals. Internal resistance R equals L0 minus L divided by L, all multiplied by capital R. We're basically comparing two distinct states of the cell to tease out its internal resistance. So let's break down exactly how you get these lengths in a lab setting. Getting this right means following these procedural steps to a T. Step 1, with the cell in an open circuit, meaning no external resistance is connected, you find your first balance point, L0. This length represents the pure EMF. Step 2, you introduce a known external resistance R across the cell, creating a closed circuit. Step 3, you slide the jockey once more to find the new, slightly shorter balance point, L, which represents the terminal voltage under load. You just plug those links into our previous formula, and you have the internal resistance. And hey, here is a golden rule. Never ever bump or disturb the primary cell during this process, because doing that could instantly ruin the accuracy of your readings. Okay, before we wrap, let's run through some quick Viva Voce cheat codes. Seriously, commit these essential precautions to memory, as they are the exact keywords examiners are hunting for in the board marking guidelines. So why do we use thick copper strips on the meter bridge? To minimize end resistance, since copper is highly conductive. Why use manganese or nichrome for the long wires? Because they have high resistivity and a very low temperature coefficient, meaning their resistance isn't going to change wildly as they heat up during the experiment. And finally, always measure your balance length starting from end A, the end where the positive terminals of your batteries are attached. Keep those in your back pocket for sure. To wrap things up, I really want to leave you with a provocative thought. We've spent this entire explainer looking at old-school wooden boards and sliding jockeys. But if a simple 19th century Wheatstone bridge principle can flawlessly balance a classroom circuit, how might these exact same concepts of null point balance and electrical ratios be used today to detect a single biological cell in cutting-edge biomedical nanotechnology? The physics of the meter bridge and potentiometer aren't just dry history. They're literally the fundamental building blocks for the quantum sensors of the future. Thank you for joining me on this explainer. Keep asking questions, and I'll catch you next time.